Hello everyone. Welcome to the ILTA Physics Problem Solving lecture. Today we are going to study one-dimensional uniform and accelerated motions together. Accelerated motion is when an object speeds up or slows down, and this type of motion is very common in our daily lives. The image below shows a subway train arriving slowly at a platform. As shown on the tracks, the velocity of the subway is pointing forward, while the acceleration used to reduce the speed is pointing in the opposite direction of the velocity. The accelerated motion we'll cover today involves objects moving in one dimension where the direction doesn't change, but the speed does. We'll look at several different types of problems. Specifically, we'll solve multi-phase motion problems, such as an object moving at a constant velocity and then accelerating, or vice versa. We'll learn how to consider each part of the motion together. Since accelerated motion makes up a huge part of classical kinematics, it's important to understand the core concepts of these problem types through plenty of practice. First, let's briefly review the basic concepts and kinematic equations needed for uniform and accelerated motion. The types of motion we've learned so far are uniform motion and accelerated motion. I've explained the detailed physical concepts in my theory lectures, so here we'll just quickly summarize the resulting formulas. To keep the equation simple, we'll assume the initial time is 0 when calculating time intervals. So we will represent the time interval simply as t in our equations. First, uniform motion is the motion of an object moving at a steady speed. The velocity of an object is defined as the change in position, which is displacement divided by time. As shown in the formula, displacement is the final position minus the initial position, and we divide this by the time interval to get the velocity. In uniform motion, this velocity is a constant value. The displacement of an object in uniform motion is calculated by multiplying the velocity by time. Therefore, the final position of the object is the initial position plus the displacement. Next are the equations for accelerated motion, where the velocity of an object changes over time. By definition, acceleration is calculated as the rate of change of velocity over time. In other words, it is the final velocity minus the initial velocity divided by the time interval. Since we are dealing with constant acceleration, we assume this value remains the same. We can rearrange this definition to find that the change in velocity is the product of acceleration and time. Therefore, the final velocity equals the initial velocity plus the product of acceleration and time. Next, the change in position or displacement in accelerated motion results from two factors. One part is the v I times t part, which represents the uniform motion if the initial speed were maintained. The other part is the 1/2 t squared part, which represents the additional displacement caused by the acceleration. Consequently, the final position of the moving object is the initial position plus the sum of these displacements. This results in a quadratic equation regarding time, which can look a bit complex. Here is an important tip to solve accelerated motion problems easily. If you know the initial and final velocity of a moving object, you can calculate the average velocity. Average velocity is literally the average speed of the object during that time interval. Therefore, the displacement during that time interval is simply the average velocity multiplied by time. This makes finding the final position much simpler. Finally, by combining these equations, we can derive a relationship between velocity and displacement that does not involve the time variable. If a problem doesn't give you a specific time information, using this velocity displacement formula is a great way to approach it. If you don't fully understand the meaning of these physical relationships yet, please go back and watch the theory lectures on constant acceleration before returning to these problems. Now, let's solve some problems involving uniform and accelerated motions together. Problem 39 involves motion that combines both uniform and acceleration. Imagine you are driving on a highway at 20 meters per second. Suddenly, you see a deer 35 meters ahead. You hit the brakes, decelerate at a constant rate, and the car comes to a stop after traveling a certain distance. Your reaction time, the time it takes from seeing the deer to hitting the brakes, is 0.5 seconds. And the deceleration from the brakes is 10 meters per second squared. The first question asks if you can stop the car without hitting the deer. The second question asks for the maximum speed you could drive on the highway and still stop in time without hitting the deer. This problem describes uniform motion during your 0.5 second reaction time, followed by accelerated motion, specifically deceleration, once you hit the brakes. For these types of problems, you just need to split the motion into two phases and use the relevant physics formulas for each. The graph on the right shows the change in the car's velocity over time. You're driving at 20 meters per second. Let's set the moment you see the deer as time 0 on the axis. For the first 0.5 seconds, you haven't hit the brakes yet, so you continue at a constant velocity of 20 meters per second. From the moment you hit the brakes, the car's speed decreases at an acceleration of 10 meters per second squared until it finally stops. Let's look at the first part, the reaction phase. We need to find the distance traveled between 0 seconds and 0.5 seconds. Displacement for uniform motion is velocity times time. So the displacement is 20 meters per second times 0.5 seconds, which equals 10 meters. Next is the braking phase, which is accelerated motion. This happens from 0.5 seconds until the car stops. Since we don't know the exact time it stops yet, let's use the formula that relates velocity and displacement without the time variable. The final velocity is 0 because the car stops. The initial velocity at the moment you hit the brakes is 20 meters per second. The acceleration is minus 10 meters per second squared. It is very important to note that the acceleration is a negative value. Physically, this means the acceleration acts in the opposite direction of the velocity, causing the car to slow down. Solving this equation shows that the distance traveled during the braking phase is 20 meters. Therefore, after spotting the deer, you travel 10 meters at a constant speed and another 20 meters while braking, for a total of 30 meters. Since the deer was 35 meters away, you luckily stopped 5 meters in front of the deer without hitting it. Now the second question asks for the maximum speed you can drive without hitting the deer. As we discussed, the total distance from spotting the deer to stopping must be 35 meters. Let's call the maximum speed Vmax. The total distance will be the sum of the uniform displacement for 0.5 seconds and the braking displacement, which must equal 35 meters. Let's express these distances using Vmax. In the reaction phase, the displacement is 0.5 times Vmax. In the braking phase, since the final velocity is 0, the displacement is the minus initial velocity squared divided by 2 times the acceleration. I encourage you to try setting up this relationship between displacement and initial velocity yourself, paying close attention to the signs. By adding the reaction distance and the braking distance, we get a quadratic equation for Vmax. Again, remember that the acceleration value must be negative because the speed is decreasing. Solving this quadratic equation gives a maximum speed of approximately 21.9 meters per second. This was a classic problem combining uniform and accelerated motions. By breaking them down and using the right formulas, you can solve them step by step. Problem 43 describes the velocity of a 100-meter sprinter over time. A sprinter starts from rest at the starting line, accelerates rapidly for the first 2.14 seconds to reach a speed of 11.2 meters per second, and then maintains that speed for the rest of the race. The question asks for the total time it took to run the 100-meter dash. Just like the previous problem, we should divide this into two parts: the acceleration phase from the start to top speed, and the uniform phase from that point to the finish line. As you can see in the velocity time graph on the right, the initial velocity is 0, and it reaches 11.2 meters per second in 2.14 seconds. After that, the runner continues at 11.2 meters per second to finish the 100 meters. First, let's calculate the distance run during the 2.14 seconds of acceleration. Even though it's accelerated motion, since we know the initial and final velocities, we can easily calculate it using the concept of average velocity. The initial velocity is 0 and the final velocity is 11.2 meters per second. So using the formula average velocity times time, the sprinter covers 11.98 meters. Now for the second part, the uniform phase. The remaining distance is 100 meters minus 11.98 meters, which is 88.02 meters. The speed during this part is 11.2 meters per second. Using the formula of uniform motion, the time taken for this section is 7.86 seconds. Therefore, the total time to run the full 100 meters is 10 seconds. This problem also featured a combination of accelerated and uniform motion, and we solved it by calculating each part separately. So far, we have solved various types of one-dimensional uniform and accelerated motion problems together. I hope you practice a lot to get used to applying the right formulas to the given conditions. That's all for today's lecture. Great job, everyone. I'll see you in the next class.